Kia ora whānau, another online tutorial today. We're looking at mechanical systems, angular mechanics, specifically through the guise of the NCEA examination question from 2017, question 2, A to D, as you can see up the top left. Let's get to it. Sylvia and Sam's spaceship spins counterclockwise on its axis as it's moving through space. The astronauts can change the angular velocity of the spaceship by firing two small rockets that are mounted tangentially as shown in our diagram. The rockets produce anti-clockwise torque. The rotation of inertia of the spaceship is 5.8 times 10 to the 4 kilogram meters squared, and we can see that little diagram just here with two rockets which are producing a torque in the opposite direction, so anti-clockwise to its current clockwise rotation. So for A, they want us to calculate the size of the torque required from each rocket to cause an angular acceleration of 2 times 10 to the negative 2 rads per second squared. So they've given us that. Okay, so we know the sum of torques is going to equal our rotational inertia times our angular acceleration. Now, let's look at the information that they've given us. They have given us the rotational inertia of the spaceship as well, and I'll just highlight that quickly, as well as the desired angular acceleration. So let's plug that into our formula. So if we go back here, we can see that that would equal 5.800 times 0.02, okay, which is going to give us our sum of torques, which equals 1160 Newton meters. So when we look at the question, we can see that it's asking for the size of the torque required from each rocket. So we've calculated the sum, which is for both the rockets. So we are going to then divide that by 2, so we get 1160 over 2 equals our torque of our individual rocket, which will equal 580 Newton meters. So that is A, done and dusted. Part B of the question, the spaceship is rotating clockwise at 0.580 rads per second when the rockets are fired. Calculate the angular speed of the spaceship after one rotation. Okay, so for B, all right, we're looking here and we're going to say they want us to calculate the angular rotation. They've told us the initial rotation and the desired, and we've calculated the angular acceleration, or use the angular acceleration, sorry, in our previous question. So we're going to use the equation lowercase omega, or our angular velocity final squared equals, and it should be reminiscent from kinematics in level 2, our angular velocity initial squared plus 2 times the angular acceleration and theta, which is 1 rotation. So we're going to plug all the information we have into there, and we get omega final squared equals 0.58 squared plus, remembering when we look at the rockets in our diagram, the rockets are going to be acting anti-clockwise, where the current rotation is clockwise. So instead of putting a plus here, we are going to use a negative. So instead of our plus here, we are going to use a negative and input the information. So it'll be negative 2 times, okay, from just above, our angular acceleration, which is 0.20 0, not 0 to 0, sorry, times 2 pi. So with that information, we can then plug that in, calculate that, and we get omega final, or angular velocity final, squared equals 0.085, meaning that our omega final, when we do our calculations, will equal 0.29 rads per second. Okay, so that's B. Now, let's look at C quickly. So, as we look at C, assume that the torque produced by the rockets is constant. Explain what happens to the size of the angular acceleration as the rockets gradually emit fuel. Okay, so we're going to be looking at angular acceleration and knowing that the rockets are emitting fuel as they're used. Okay, so what we're going to think about for C is we're going to think about our understanding of torque, inertia, and angular acceleration. Now specifically, if we put in the equation T equals IA, torque being our, or T being our torque, I being our rotational inertia, A being our angular acceleration, assuming that the torque produced remains constant, we want to find what happens to our acceleration. So we're going to think about what would happen to inertia as the mass changes. Now, assuming that our spaceship is cylindrical, rotational inertia would equal half mass r squared. So as we're using fuel, our mass would be decreasing. Okay, which means that our rotational inertia would be decreasing. Now, if our torque is constant, produced by the rockets, but the inertia is decreasing because our mass is decreasing, our angular acceleration must be increasing. So what would we say? We could say, as the rockets emit gas or fuel, the total mass of the spaceship would decrease, okay, the mass of the system. This will cause the rotational inertia here to decrease. Torque being constant, our angular acceleration would gradually increase. So as mass decreases, this causes our inertia to decrease and our angular acceleration to gradually increase while torque remains the same. So that's C. Let's have a look at D. So, sometimes later, the spaceship is rotating freely at 0.450 rads a second. When the rockets turned off, as shown in diagram 1 here, the spaceship's photovoltaic cells are then extended out from the spaceship, causing the rotational inertia to increase by this given amount, which is 2.74 times 10 to the 3 kilograms meters squared. Okay, so we have our diagram here, and we can see that it is rotating and it is moving, or it is deploying its photovoltaic cells. One thing we're going to note from this, okay, is that in this situation, we are now moving our mass outwards, and that's poor. Okay, we are moving our voltaic cells outwards, which is going to mean our mass, or our center of mass, is going to be the same, but more of our mass is going to be around the outside rather than central. And we know this is going to have an effect on our inertia. Okay, it's going to increase it. So, explain why, for I, the period of rotation changes as the voltaic cells are extended in diagram 2. Okay, so as we discussed, as the mass moves further from the center of rotation, because the center of rotation would have been previously the center of our spaceship, okay, as we deploy those voltaic cells outward, right, the mass or distribution of mass is moving away from our center of rotation. This causes the rotational inertia to increase. Because there is no outside torque applied, angular momentum is conserved. Okay, so we can use that in our next bit. We know that the angular momentum is conserved. If we know that inertia is increased, angular momentum is conserved, we're going to be thinking, all right, cool, something needs to change, and that's going to be the velocity. Okay, it's going to slow down. And calculate the period of rotation when they're fully extended. We're going to do that next. So there'll be a decreased period, or an increased period, sorry, because our velocity will have decreased. Let's have a look. Let's get to it. dii. Okay. For dii, we know that our angular momentum, L, is equal to our rotational inertia times our angular velocity. Okay. And we know, as we discussed, because there's no torque acting on the spaceship, or no external torque acting on the spaceship, our angular momentum must be conserved. So our Li is going to equal our LF. Oh, I don't know why I did such a big F there. Get rid of that real quick. Okay, so our initial angular momentum is going to be the same as our final angular momentum because it's conserved. Okay, what can we do with that information? Well, we're going to use this equation here for our two situations, okay, to calculate what's going on. So we know for our first instance, okay, that Li, or L, is going to equal, or Li equals the information provided. We have our rotational inertia from the top, which is 5.8 times 10 to the 4 times our angular velocity, which we have from earlier, which is, which we have been provided in the question, which is 0.450. That is going to equal our momentum final, which will equal new rotational inertia, which is going to be what it was previously, 5.8 times 10 to the 4 plus the increase in inertia, which is going to be 2.74 times 10 to the 3, okay, that being our new I, okay, times our angular velocity, of which we want to calculate this here. Okay, so with that information, if we rearrange the equation and divide the left side by this number here, okay, and I won't do that because I'm running out of space, we get an angular velocity of 0.43 radians a second. Okay. With that in mind, we can think about our equation for angular velocity, which we know is 2 pi over t being our period. Okay. We can use this equation to rearrange this equation to now calculate our period. So we have a different angular velocity. Okay, angular velocity has decreased as our inertia has gone up, which means our period has changed. We can rearrange these equations to get t equals 2 pi over our new angular velocity, okay, which will equal 2 pi over 0.43 0.43. And we get our new period of 14.6 seconds. Okay, well, that looks a bit like a 5, so let's get rid of that. Cool. 14.6 seconds as our final answer. The new period of rotation once those cells have been extended. So, what have we done here today? Okay, we've calculated torque with the information provided. Right? We've used our understanding of angular velocity and acceleration to calculate an increase in angular velocity. We've used our understanding of inertia and torque to discuss what would happen when mass of an object changes, how that would affect the inertia and acceleration of an object as it's still accelerating or is still having a torque applied. We have then looked at period of rotation changes as mass shifts away from the center. So how shifting mass will change our inertia, okay, and how that will affect our rotation and our velocity, or angular velocity, and using our understanding of angular velocity to then calculate the change in period after that inertial change. So, quite a lot there, team. Hopefully you found this helpful. Hopefully you can use this as a guide to get out there and try some relevant NCEA questions. As always, give it your best shot and have a lovely day.